Hello everyone, I'm Mingzhu Shen from Beijing Institute of Technology, China. The topic of my speech is deep learning-based program generation from requirements text. Are we there yet? My speech is divided into 5 parts. It's an outline. The first part of our speech is motivation. To release human beings from time-consuming software development, automatic code generation tasks have become a research hotspot. The key insight of such approaches is that given a corpus of software requirements and their codes, deep learning may learn how to translate software requirements into source code. Approaches have been reported to be highly accurate. For example, SNM reaches a high BLU 0.845. In contrast, the widely used Google Translation results in much smaller BLU 0.4 in translating English into French. The reason for the above situation, data size is an important factor. It's well recognized that high-quality data sets are critical for learning-based code generation. All deep learning methods require large-scale data sets for training. These are the data sets that are now used to train deep learning methods. Dataset includes simple requirements and corresponding implementations. As can be seen from the example on the previous page, we observe that existing datasets are small. The average length of the Zhang source code is 33 characters. Lack of diversity. Dataset HS is composed of cells from a single software project, which results in poor diversity, and significantly different from real-world software requirements. Natural language descriptions in dataset Canala are how-to questions extract from Stack Overflow instead of real-world requirements. To this end, we propose a new dataset. Here, we present the overview of our approach. We cross the code from the programming context platform. After that, we remove code duplication, static checking, and cross-validation to obtain the final dataset. We collect data from 2 programming context platforms, CodeForces and HackerEarth. With a Python-based crawler, we collect software requirements from the selected platforms. We also collect their corresponding codes that have passed all of the associated test cases. At the same time, for the next code evaluation, we collect the test cases together. Then we filter the code. We remove the duplicate tasks and code, and filter out outdated submissions by compiling them. After data filtering, some bug submissions can still pass test cases. To further improve the reliability, we carry out cross-validation by software testing. First, we automatically create test cases with first testing. For each test case, we automatically run each of the submissions with test case. If the submissions result in different outputs, we manually check the results and remove the buggy submissions. As our resulting dataset, the dataset has more programs, and the length of the requirements and programs is longer. It also has multiple implementations and general-purpose programming languages. The third part is our empirical study. We select 5 state-of-the-art approaches for the evaluation on our dataset. They come from 3 research groups. The first research question: investigate how accurate are the state-of-the-art approaches on the new dataset. We randomly select 300 texts as testing data, 200 texts as validation data, and the other as training data. Then we pre-process the dataset and train it. Finally, we evaluate the quality of generated source code. From this table, we can find switching from existing datasets such as HS and Zhang to our new dataset reduces BRU significantly. The value of BRU does not exceed 0.2. This is a comparison between reference and generated code. First, most statements are not generated successfully. Second, most of the generated source code is irrelevant. The second research question: investigate how often do the generated programs pass syntactic checking. Our checking is carried out from 2 angles: syntactic and execution. Syntactic checking is static checking using a compiler, while execution checking is running dynamic checking with test case. From this table, we first observe that most of the programs generated by AST-based approaches, such as SNM, tree-to-tree, and tracks, performance better than other approaches on syntactic checking. The second observation is that only a small part of the generated programs could be executed without exceptions. The lowest execution success rate is only 3%. The first part, online source. All in all, we conduct a dataset fitting the real-world code generation scenario and present new assessment tools. We also provide API interface to access these resources. The source address is shown in the hyperlink. Our API is suitable for 3 situations. We provide API for retrieval data on Circle. We can use these APIs to query tasks code and test cases. And we also provide API for evaluating and computing code metrics, such as BRU. In addition, we also provide methods for pre-processing tasks and codes. At last, we have some conclusions. First, when conduct a large-scale dataset, its content is more diverse. Second, we provide an assisting tool to measure the quality of generated programs. Last, evaluation result shows deep learning-based program generation requires significant improvement in the future. That's all. Thanks for your listening. Does anyone have any questions?
Hi again. We are now with the second paper of our session, and we have with us Hui Liu and Yu Shen, both authors of the paper, and they are going to answer any questions you may have. Okay, so for the moment, we have like 3 questions. I will start with the first one. So Jiang is asking, what is the major reason for poor performance of the evaluated approaches on your new data set?
Okay. First, thanks for your question. Our analysis is that there are multiple reasons for this situation. First, some special characters in existing datasets facilitate learning-based code generation. For example, the requirements in Django are quite similar to their implementations. As a result, learning-based approaches may achieve high performance by copying tokens from requirements to generated programs. In each case, different programs are highly similar to each other, so which also significantly facilitates code generation. Second, the requirements in our dataset are much more complex than the existing ones. A great challenge in code generation in natural language understanding, such as to understand the requirements. The longer the requirements are, the harder understanding is. Compared to existing datasets, our dataset is composed of much longer and much complex requirements. The average length of such requirements is 185 tokens, compared to 14 in Django. Third, the diversity of our dataset has a significant negative impact on the evaluated approaches. Such approaches have been trained in a specific domain with similar requirements. However, our dataset has very diverse requirements with no common tasks. As a result, except for the generic programming skills, little could be learned about the implementation of specific tasks. However, little could be learned about the learning the generic programming skills is highly changing. As a result, the performance of generation is reduced. Fourth, the size of our dataset may have prevented the evaluated approaches from reaching their potential. In total, the dataset is composed of 16,673 requirements code pairs. Comparable to other datasets have been other evaluated approaches. First is our tuning hamper parameters. I think is a reason for approaches performance not so good on our new dataset. So it have very multiple reasons.
Very much. We have another question from Miroslav Staron. I wonder if so many of the suggestions were not relevant, how many of the execute programs were correct with respect to requirements?
Okay, it's a very good question. In fact, a very small part of the program, general programs can be executed. According to our data, a table on a paper, is less than 10% of the programs can be executed without any errors or exceptions. And among such 10% of executable programs, none of them can pass any test cases associated with the task case. So I suppose none of them are exactly correct with regards to requirements.
For your answer. Jiang has some more questions, so I will go one by one. Or, well, I don't know, since they are related, perhaps I can read you all of them. So first question is, what should we do next to improve the state of the art in program generation? Another one is, have you tried to evaluate the state of the art approach to real software applications on GitHub or SourceForge? How did they perform?
Okay, thank you. Very interesting questions. The first question is that what should we do to improve the state of the art? I suppose that it's very difficult to generate our programs according to the text requirements, because it's exactly difficult to understand the requirements. That's very lengthy requirements. For example, in our data set, we have programming tasks for students. So compared to the real programs, such requirements are very simple. However, state-of-the-art natural language processing technologies cannot yet understand the meaning of these requirements. And as a result, in our paper, we have replaced the requirements with noise data and repeat the evaluation. Surprisingly, we found that the performance of the evaluation do not change so much because of the replacement of the normal requirements into noise. It's suggesting that our technologies cannot yet understand the requirements. So I suppose to improve the state of the art, we should find ways to improve the understanding of natural language requirements. I think it's the most important thing. And what's the second question?
Okay. Have you tried to evaluate the state-of-the-art approach to real software applications on GitHub or SourceForge? How did they perform?
Exactly, no. Because ACM programming tasks are simple, much simpler than such real-world software programs. And we have found out that state-of-the-art approaches cannot yet generate programs for simple tasks. So I don't think there's any chance for such approaches to generate real programs in the GitHub or SourceForge. It's unlikely to happen in the near future. So I suppose maybe you can try later, but we have not yet tried that. Thank you.
For the moment, there are no more questions, but we still have 2 minutes left. So I'm going to ask you one question. First of all, my congratulations, because I think you have done a great job. I think it's a very, very interesting research. And my question, based on the results of your work, how far do you think are we from DL-based program generation? Do you think it will ever be feasible, or will it remain as an unfulfilled promise? So what is your feeling about that?
Thank you. Very interesting question. I suppose that in the near future it'll be very difficult, but in finally we can manage a way to generate simple programs, especially with high quality, large training data set. And that is what we are doing. That's we have to build a large scale, high quality data set so that we can attract a lot of researchers, especially those in the field of artificial intelligence, okay? Maybe outside of the field of software engineering community. So all the researchers in the world, especially those working on AI, can come here to work on our data set, and it could be potentially we can find our ways to understand how we can generate programs, how we can understand the requirements, software requirements, okay? Because, as we can see it from our paper, most of our baseline approaches came from outside software engineering community. They came from field community of AI, like ACL, ICML, or what, okay? So to researchers in the field of software engineering community. So I suppose with our data set, we can attract more researchers to solve the problem in our software engineering community to find ways to generate programs based on the test requirements. I suppose it's potentially room for it.
Hello everyone.